Okay, so today we're talking about how we can reconcile the regression equation from a model that contains spline terms. And so this isn't always very straightforward, and I always get confused in it myself. So typically, when we have a linear regression model or a generalized linear model, we're assuming that the relationship between the independent variable and the outcome are linear. But oftentimes, we want to relax that assumption and capture some sort of known or unknown nonlinear trend between those variables. And so we can add these spline terms that basically give the model the freedom to sort of find curvature in the relationship, but it comes with a cost of more parameters in our model. What we concern ourselves with here is how we actually take the model output and produce an actual written out regression equation that we can say plug in our inputs and get the correct predicted value out of it. So oftentimes in R, you'll look at the summary of your model and you'll get some parameter estimates, but it's not straightforward what those actually represent. It's not as simple as just plugging in your raw input value and summing the parameters together like you would in a normal regression equation. We actually have to dig deeper into this spline process and figure out things like what were the not locations, was there normalization involved, and things like that, so we can adequately recover this transformation that was made onto your input variable and map it back to being something on the scale of the raw value, so that we can then take this equation and say embed the model into a web application or something. If we can write it out explicitly just into a mathematical formula, our model still maintaining this flexible nonlinear structure is super lightweight, and we can, for example, program it in Excel instead of having to rely on R's predict function or something like that, where we need, say, an R Shiny app running where we can use R runtime. We don't want to do that. We want to be able to just have our model as lightweight as possible. So this is a way to help us easily represent our complex nonlinear model in a simple formula like we would with any other regression model. So in the rest of this video, we're just going to walk through the article and specifically the R code that generated the differing plots, and we'll kind of talk through those things. We're in RStudio, and we're just going to start with loading some packages from the tidyverse and get a data set. So this heart disease data set is from the cheese package. We're interested in modeling the relationship between age and blood pressure, and so we'll just start with a scatter plot. Ultimately, what we want to do is start with a very simple model and work our way up to something more complex with splines involved. And we can see maybe there's something increasing here, maybe it's curving, there's a lot of variability. First, we are just fitting a simple linear regression model, and if we look at the estimates from that, if we want to recover our regression equation here, it's just as we would expect. If we want to get a predicted blood pressure, all we need to do is take our age value and plug it in to the formula, multiply by the slope, and add the intercept. And we can overlay that line to our plot. And so here, this little code snippet, we are just comparing, okay, to make sure that we can reconcile our predictions. If we just hard code the model as we expect it to be versus what R does internally with the predict function, do we match? And 100% of the fitted values match as we would expect. So then we go into, okay, now we want to introduce some more flexibility. We want to allow this line to not be a line. Maybe it'll be a curve depending on what sort of relationships it finds. And so we're using this RCS function from the RMS package. And here we're specifying a restricted cubic spline on age with 3 knots. We can add more knots if we want, which is going to add more flexibility to the fit at the cost of more parameters in the model. But using 3, that's pretty standard. So if we fit that model, we get something like this. And so now our model says we have an intercept of 94.8, and we have this parameter on age 0.7016, and then this parameter on age prime, whatever age prime is, negative 0.1854. Here we're just adding a fitted value using the predict method. So these are the correct fitted values from R internally. There's a little bit of bend. It actually doesn't go upward like we might have thought. It goes up and then a little more flat. But anyway, so it's fitting this more complex model, and in this case a linear model, would probably be sufficient. Point here is that if we go back to the summary, if we wanted to recover what this regression equation actually is on the scale of age, because again, age is our only input here. And so if I wanted to get a predicted value for blood pressure given in age, what do I actually plug into my formula here to get that? I can't just take 94 plus age times 0.7 plus age times negative 0.19. That's going to give me nonsensical results. And so you can see that BP1 is the correct predicted value from R internally using the predict function. BP2 is this knowingly wrong calculation, which we're just taking the intercept plus the first age parameter times age plus the second age parameter times age, and that's wrong. And so we can confirm that 0% of the fitted values match. And so we need to do some more work in order to create an actual formula on the scale of age where I can just input an age and get an output. And that's where these knots come into play. So when we're fitting a spline term, it uses these knot locations that determine kind of where we're going to allow bends to take place. This RCS function uses the 10th, 50th, and 90th percentiles of your input distribution as the knot location. So we can see there's a knot at age equals 42, 56, and 66. And we can confirm that those are those quantiles. So this is where some of the math comes in then. If we look at the blog post and kind of write this out more explicitly, we have to use these knot locations in what's called a truncated power basis at each knot, which is basically just using this formula where we take the difference between the input value age minus the knot value and cube it. If it's greater than 0, that's the value you use, otherwise you use 0. And you do that at each knot location to come up with some sort of transformation. Becomes this kind of complex formula, this truncated power basis for the first knot minus some difference between the knot locations times the truncated power basis at the second knot, plus again some sort of ratio of the differences between the knot locations times the truncated power basis at the third knot. And as you can imagine, the more and more knots I add, the more and more flexibility or parameters I'm adding to my model, this is only going to get more complex. So this is what we need to start to work with to get our model into a coherent formula where we can just plug in age and get something back. Okay, so now if we figured out this part and we define this age spline as, if we just plug in those knot locations into this formula, is that all we need to do? Now, is our model then just the intercept plus that first age coefficient minus the second age coefficient in the model, the spline term, times this complex spline value? So we're computing this age spline, and now we're going to test out what we just saw and see if that's right. So now if we check the concordance, it says only 12% of fitted values match. So I guess we got some of them right, but obviously it's not correct based on what R gives internally with the predict function versus what we just tried doing with this complex spline formula. We're still getting the wrong answer. So we need to figure out why, but we got some of them right, so maybe we're on the right track. And so this is where the final piece of it comes in, and there's something called a normalization factor within these functions. So if we look at some documentation for this rcspline.eval function within the hmis package, which is just a kind of a subpackage of RMS basically, there's this parameter or argument called norm, and we can see that the default value of norm is 2. If we look here, it says use value of 2 to normalize by the square of the spacing between the first and last knots, the default. And so when we ran RCS, the RCS function on age, by default it did this sort of normalization by the square of the spacing between the first and last knots. So in order to reverse engineer what it did internally to again get our regression equation back on the scale of age in years, we need to recover this normalization factor and multiply that through things. So if we look back at the blog post, the square of the spacing between the first and last knots, so if we just calculate what that is, ends up being 66 minus 42 squared is 576. All we end up needing to do is then divide the parameter value in our model output that R gives us, divide that by this normalization factor before we multiply it by this spline term. So here we get the normalization factor, and then we end up doing just that. So again, if I look at this model again, I'm taking the intercept term, 94.8, plus the first age coefficient, 0.7016 times age, again on the raw age scale, plus the second coefficient, negative 0.1854, and dividing out this normalization factor, and then multiplying it by this age spline term, which again was this complex expression. So if we add that to our data frame, we look, 100% of the fitted values match. Now we can write out the final formula again on the scale of age, where blood pressure is equal to 94.8 plus 0.7 times age, plus and this parameter estimate from R divided by the normalization factor times this complex spline transformation of these truncated power bases. With one parameter extra in our model and wanting to allow for our simple linear regression model to find some sort of curvature, we added this much complexity to it. But the nice thing here is this is all just simple math calculation, and so I just need to plug in my age value in years into this formula, and I'm going to correctly get the appropriate predicted blood pressure. So now I can take this formula and easily embed it in whatever tool I want.